3 miles below the Pacific, Mission Director Dale Nielsen oversees an operation where failure means destruction. His orders are clear. If the hull breaks where Soviet eyes can see it, scuttling charges will destroy the evidence and everyone aboard before the first photograph surfaces. The problem is the hydraulic system. The pressure gauges are climbing into the danger zone. The steel claw lifting a massive section of Soviet submarine, designed to handle roughly 1,700 tons, was never meant to hold this long. Above him, a Russian trawler holds station, close enough that Nielsen can hear its screws through the hull. Below, swaying in absolute darkness, a crushed graveyard believed to contain the submarine's nuclear arsenal, ballistic missiles, and torpedoes, American intelligence has never seen intact. The Soviets think they're watching a mining operation. They have no idea the ship beneath their guns is puppeteering the largest theft in naval history. But Nielsen isn't thinking about history. He's thinking about the engineering limits. The claw's marging steel is being pushed beyond its design specifications, approaching the threshold where structural failure becomes catastrophic. No cameras survive at this depth. No backup systems exist. Just Nielsen, the monitors, and pressure readings that shouldn't be climbing. The numbers spike into the critical zone. Then he hears it. A sound like a gunshot echoing through 3 miles of black water. Metal screaming as the claw begins to tear. Earlier that day, the Hughes Glomar Explorer held station over coordinates the Soviets had briefly searched in 1968 before abandoning the effort. 6 years before this recovery attempt, Dale Nielsen and the control room team began lowering Clementine, a pipe-string claw weighing 2,000 tons, toward the wreck site of K-129 at 16,500 feet. The descent took approximately 15 to 18 hours, with each segment of pipe bolted in sequence as the winch paid out cable at 15 feet per minute. The claw itself was hidden inside the Glomar's moon pool, a 199-foot opening cut into the ship's hull, so no satellite or surface observer could photograph it. As Clementine descended into the abyss, Nielsen's team monitored the operation through a sophisticated array of deep-sea cameras and strobe lights, tracking sonar returns to confirm position. They were navigating a graveyard in near-absolute darkness, relying on technology pushed to its limits. Clementine's hydraulic claw had 8 steel tines designed to cradle the submarine hull like fingers closing around an egg. Operators had to achieve even pressure across all contact points, working with limited real-time feedback at such extreme depths and no way to adjust grip once the ascent began. The tines were controlled by hydraulic lines running 16,500 feet down the pipe string, with pressure regulated from the surface. A grip too weak would drop the submarine. A grip too strong would crush the corroded hull and spill debris across the seafloor. Nielsen's team relied on sonar and available imaging systems to estimate hull position, then closed the claw in increments, waiting minutes between each adjustment for pressure readings to stabilize. Operating under intense constraints with one attempt to succeed, mission records indicate the team worked largely without tactile feedback. If they missed, the Soviets would notice the Glomar holding station and investigate. 2,000 yards east, the Soviet trawler SB-10 held station. Its mission was routine: monitor Western vessels in international waters and report unusual activity. The Glomar's crew knew the trawler had radar, radio intercept gear, and eyes on deck. To maintain the mining ship cover, the crew ran a choreographed routine. Sample drills lowered empty buckets to shallow depth. An ore processing crusher ran at irregular intervals, grinding rock hauled aboard weeks earlier. Deckhands moved equipment in patterns consistent with mineral extraction. None of it connected to anything below the waterline. The charade had to be seamless, because one inconsistent radio transmission or visible Navy asset would trigger a Soviet boarding party. Below deck, CIA cover officers monitored the trawler's movements and rehearsed responses to inspection scenarios that would end the mission and create an international incident. Nielsen gave the command to close the claw. Hydraulic pressure climbed from 0 to 6,200 psi over the course of an hour. The tines locked into position, and sonar showed the target was captured. But the team had no way to verify grip quality or hull deformation. They could not see stress fractures forming at the contact points. They could not measure load distribution across the 8 tines. They could not confirm whether the corroded hull would hold under its own weight during ascent. The mission clock started. 8 days to lift K-129 16,500 feet at 3 feet per minute, with the Soviets watching and the claw's grip untested at crushing depth. Nielsen logged the pressure reading and initialed the go decision. The winches began to turn. At 16,500 feet, seawater pressure exceeds 7,300 psi. That is well beyond the rated tolerance of commercial hydraulic hoses, which are specified for depths under 10,000 feet. Clementine's system used experimental reinforced lines developed by the Deep Submergent Systems Project, never tested at this depth with load. According to available records, the claw's hydraulic actuators were powered by onboard electric-driven pumps, while surface pumps transmitted high-pressure water through the pipe string for the breakout legs that would free the submarine from the seafloor. The reinforced lines had to resist external seawater pressure that could collapse them or force seawater into microscopic cracks. The engineers knew the hoses would deform under sustained pressure, but they had no field data on how much. Every hour the claw remained at depth increased the risk of fatigue failure. Engineers were concerned that a loss of hydraulic pressure could compromise the entire recovery operation, though the system was designed with redundancies to prevent catastrophic failure from a single breach. The claw was designed to lift 4,000 tons in theory, but K-129's hull was corroded, structurally compromised, and filled with silt. The submarine had rested on the seafloor for 6 years. Salt water had eaten through the outer hull plating, weakening load-bearing frames. Any uneven load distribution would bend the tines or tear the hull before it cleared the seafloor. The engineers had no way to inspect the hull's condition before the lift. They relied on sonar returns and pre-mission estimates of corrosion rates. But those estimates assumed uniform decay. In reality, stress concentrations from the original sinking had left weak points that could fail under tension. If the hull tore during ascent, debris would scatter, and the Soviets would investigate the Glomar's prolonged stationary position. Standard salvage operations allow multiple attempts and surface repositioning. Project Azorian had one attempt. If the claw lost grip or the hull disintegrated, the debris field would scatter and the Soviets would investigate. There was no margin for error and no second pass. The Glomar could not reposition without breaking the mining cover story. Soviet satellites photographed the ship's position daily. Any deviation from the planned mining grid would alert Moscow that the operation was not commercial. The mission's covert nature forbade the use of Navy submersibles, surface buoys, or encrypted communications with DSSP engineers ashore. All decisions had to be made by the civilian crew in the Glomar's control room using indirect sonar data. Nielsen and mission director Dave Sharp knew they were operating at the edge of salvage capability, with none of the tools that made deep recovery survivable. The Glomar Explorer arrived at the target site on July 4, 1974. Nearly a month later, on August 1st, the massive hydraulic lift system began raising the claw. The pipe string rose smoothly, and sonar confirmed the target was moving. K-129 was off the seafloor. But they had a problem. The ascent would take 8 days. 8 days with the Soviet salvage tug SB-10 shadowing them, frequently challenging the crew via radio and signal lamps. 8 days to pull a Soviet submarine through 3 miles of ocean while maintaining the mining routine? Every hour the claw held was another hour the Soviets could decide to investigate. For the first hour, every system operated within normal parameters. Hydraulic systems maintained the massive pressure required for the lift. Load sensors showed expected tension. Below, in the control room, Nielsen watched the depth gauge count upward. 16,480 feet. 16,460 feet. On deck, The crew lowered sample buckets and ran the ore crusher. The performance continued. But the clock was running. The lift progressed steadily during active cycles. The submarine was coming home. If they had 8 days before something went wrong. For now, the claw was holding. 6 hours into the lift, hydraulic pressure in the starboard tine circuit dropped from 6,200 to 5,900 psi. The operator increased pump output to compensate, but pressure continued to decay. The hoses were stretching under sustained load and changing depth. As external seawater pressure decreased with Ascent, the hoses expanded slightly, absorbing hydraulic fluid volume and reducing the force transmitted to the tines. The engineers had predicted this effect, but the decay rate was faster than models suggested. Nielsen ordered a pressure increase to 6,400 pounds per square inch, closer to the hose's burst threshold. The starboard circuit stabilized, but now the safety margin was gone. Any further pressure loss would require pushing beyond rated limits, risking catastrophic line rupture. Sonar returns showed an asymmetric shape. The submarine's bow was angled 15 degrees higher than the stern, indicating uneven load distribution across the tines. The aft section was heavier than expected, likely filled with silt and seawater, pulling the stern downward and concentrating stress on the forward tines. Nielsen ordered a reduction in ascent speed to 2 feet per minute to avoid dynamic stress. Slowing the lift reduced inertial forces, but it extended the mission timeline and increased the risk of Soviet detection. The Glomar would remain stationary longer, requiring the deck crew to sustain the mining charade for additional days. Sharp approved the decision. They could not afford to let the hull shift inside the claw. The angle was already at the edge of safe tolerances. At 12,000 feet depth, a sonar technician reported a new acoustic signature. Faint metallic groaning, consistent with hull deformation. The sound repeated every few minutes, each time slightly louder. The team could not see the claw, could not adjust grip, and could not stop without losing depth control. Stopping the winches would leave the pipe strings stationary in ocean currents, inducing sway that could shift the load and worsen the deformation. The only option was to continue the ascent and hope the hull held together. Nielsen reviewed the hydraulic logs. Pressure was stable at 6,400 pounds per square inch. The tines were locked. But somewhere, 3 miles below, steel was bending under forces the engineers had never been able to test. The groaning was K-129 speaking. They just didn't know what it was saying. The SP-10 remained on station, conducting routine radio checks. The Glomar's deck crew continued the mining charade, lowering empty sample buckets and running the ore crusher at irregular intervals to simulate extraction work. CIA cover officers monitored Soviet radio traffic for any sign of suspicion. There was none. The trawler's crew saw what they expected to see, a slow-moving mining vessel working a deep ocean manganese claim. They had no idea that 30 feet below the Glomar's waterline, a control room team was listening to a Soviet submarine groan as it rose from the abyss. The surface routine and the subsurface crisis ran in parallel, each second of calm on deck masking the mechanical failure building below. Sharp knew the cover had a time limit. If the lift took too long, the Soviets would ask why a mining ship stayed on one spot for 10 days. Nielsen's eyes locked on the pressure gauge. The numbers were dropping. Not from a leak, not from a pump failure. Something worse. According to some technical accounts of the mechanical failure, as the claw ascended and external pressure decreased, the hydraulic hoses expanded, absorbing fluid volume. The force transmitted to the tines was weakening. The claw was loosening. Rising toward the surface with 2,000 tons suspended beneath it. The engineers had understood this behavior in principle, hoses expanding under pressure, the physics predictable and unavoidable. But they had never tested it at scale, never proven it could hold a load this massive in open water. At 16,500 feet, external seawater pressure had compressed the hoses, maintaining effective grip force at the tines. The system was designed for that depth, and initially it worked. Now, with every foot they climbed, according to these accounts, The grip was slipping. The control room could compensate by increasing pump pressure, but according to technical accounts, the system was already operating at extreme levels that tested the limits of the experimental hoses. Engineers had established operational boundaries before the mission, with safety margins calculated to prevent catastrophic failure. But Nielsen was pushing into uncertain territory, and the ascent was only halfway complete. As the submarine rose through the water column, the changing pressure differential placed increasing stress on the recovery vehicle's systems, with each foot of ascent altering the delicate balance the hydraulic lines had to maintain. K-129's hull, corroded after 6 years on the sea floor, could not distribute the claw's point loads evenly. Stress concentrated at the time contact points, initiating microfractures that propagated as the hull bent during ascent. Steel that would have been ductile when the submarine was new had become brittle from saltwater corrosion and pressure cycling. The claw's grip force, even when stable, applied thousands of pounds per square inch at 8 discrete points. Pre-mission estimates assumed uniform hull strength, but corrosion does not decay uniformly. Stress concentrations from the original sinking, where the hull buckled or tore, had left weak points that could fail under tension. As the hull shifted inside the claw, those weak points were the first to crack. The engineers could not inspect them, could not reinforce them, and could not predict where the next fracture would occur. Nielsen stared at the readouts, watching the numbers betray him in real time. Grip force dropping, hull shifting inside the claw, and with each shift the point load spiked, driving fractures deeper into metal that couldn't take it. Deeper fractures meant weaker hull. Weaker hull meant more shifting. More shifting meant higher loads. The cycle was feeding on itself. Could they break it? According to engineering accounts, tightening the grip risked bursting the hydraulic hoses. Inspect the hull. Impossible. Not from up here. Pause the ascent. That would only induce sway, make the shifting worse. They had one lever left. Ascent speed. Slow it down, buy time, maybe the hull holds together long enough. But slowing the lift wasn't stopping the cycle. It was just stretching out the clock. The engineers had designed Clementine to lift an intact submarine. What they had in that claw was a corroding shell tearing itself apart under its own weight. Nielsen knew the feedback loop was driving toward structural failure. The question burning in his mind: could they reach the surface before it did? During the recovery attempt in early August 1974, sonar picked up a sharp acoustic transient, a crack. Hydraulic pressure in 2 aft tines dropped to 0 instantly. The remaining forward tines were subjected to extreme stress, far exceeding their design limits. Technical monitors observed the pressure surge, then the collapse. The control room went silent. Every operator knew what the numbers meant. The submarine was breaking apart, and the pieces were falling. The sonar technician tracked the aft section as it began its descent back toward the seafloor, tumbling in slow motion through 3 miles of black water. Impact would create a debris field visible on Soviet sonar if the SB-10 was listening. The mission had just become a race between secrecy and gravity. The control room watched sonar returns as the aft 2/3 of K-129 fell back toward the seafloor. The section, roughly 100 feet long, contained the missile silos and cryptographic machines the CIA had prioritized. It tumbled as it fell, shedding debris, hull plating, interior equipment, silt. Impact was expected to scatter wreckage across a wide area. If the SB-10 detected the acoustic signature of the impact, they might investigate the debris field. The mission's cover would collapse. Sharp and Nielsen had minutes to decide whether to abort, release the forward section, and surface immediately, preserving the mining story, or continue the lift with a partial hull that might tear further and drop evidence into open water where Soviet cameras could photograph it. Sharp and Nielsen faced the abort decision. Release the remaining forward section and surface immediately, or continue the lift with a partial hull that could fail at any moment. The forward section of K-129, reportedly containing the forward torpedo room, remained in the claw. According to declassified CIA histories, the conning tower and most critical intelligence materials had been lost when the submarine broke apart. But the remaining tines were now overstressed. Any further hull failure would drop what they had recovered into open water where the Soviets could photograph it. Sharp made the call. Continue. The intelligence value of what remained in the Claw justified the risk. The crew had spent 4 years building Clementine and 8 days lifting the submarine. They would finish the mission. Nielsen logged the decision and ordered the Ascent to resume at 2 feet per minute. The Claw, now holding only a portion of the submarine, was still at 140% of rated capacity. The Ascent resumed. But everything had changed. The Glomar's winches turned at 2 feet per minute, slower than before, minimizing dynamic stress on the overstressed tines. Nielsen stared at the hydraulic readout. 6,400 psi. Just below the burst threshold. One pressure spike, and the entire forward section drops into the abyss. Sonar showed the forward section rising steadily. No further acoustic transients. But the team knew what the instruments couldn't show them. The Claw was operating beyond design limits. The tines were bending under load. The hull was weakened by the initial fracture. And somewhere, 3 miles below, the aft section lay scattered across the seabed, leaking radiation into the Pacific. Any sudden shift or current surge could trigger a second failure. The crew could do nothing but watch the depth gauge count upward and hope the Claw held together for 3 more days. 3 more days of waiting. 3 more days of praying the metal doesn't fail. And above them, Soviet trawler remained on station, unaware that the submarine was now inside the moon pool's approach corridor. Unaware that half of it was already gone. The ascent continued without further failure. On August 8th, the forward section of K-129 approached the Glomar Explorer's moon pool. The submarine had to pass vertically through a 199-foot opening in the ship's hull while swaying on cables in ocean currents. Nuclear torpedoes were still aboard. A collision with the hull edge could rupture a warhead, flooding the well deck with radiation and killing the recovery crew inside the sealed chamber. The Moonpool team, waiting below deck, had no real-time communication with the control room. They relied on timed signals and mechanical stops to guide the Claw through the opening. Nielsen reduced ascent speed to 1 foot per minute for the final approach. The Claw entered the Moonpool at 6:40 a.m., clearing the hull edge by less than 4 feet on the starboard side. The Claw released inside the sealed well deck. Hydraulic pressure dropped to 0 as the tines opened, and the forward section of K-129 settled onto support cradles. The Moonpool crew secured the hull with tie-down cables and activated ventilation fans to clear seawater vapor. Recovery teams entered wearing radiation suits and carrying Geiger counters. The first priority was the torpedo room. 2 nuclear torpedoes, each roughly 20 feet long, lay in flooded launch tubes. According to available records, the torpedoes had been damaged by extreme ocean pressure, though recovery teams carefully extracted them and transferred them to shielded containers. Next came whatever documents could be found in the bow section. Some paper materials had surprisingly survived the depths, though the code room itself, located in the unrecovered center section near the conning tower, remained on the ocean floor. By the end of the first recovery day, the most sensitive materials from the bow were secured, and the crew began documenting the interior. The recovery teams descended into the forward torpedo room, not knowing what they'd find. 2 nuclear torpedoes lay intact, the first Soviet warheads American engineers had ever examined. Disassembly revealed yield characteristics, fusing mechanisms, and safety interlocks that would influence U.S. defensive planning for the next decade. Some water-damaged documents were recovered, though most historians believe the primary cryptographic materials, the code room and current cipher machines, were lost with the aft section that fell back to the ocean floor. Each discovery confirmed Soviet naval doctrine and warhead design previously known only from theoretical estimates. But something had gone catastrophically wrong at 8,000 feet. The Claw had failed. The aft section, containing the missile silos and cryptographic machines, was lost. The forward torpedo room had yielded enough intelligence to justify the mission's cost, according to the CIA's declassified assessment, though it fell short of the original objective. The CIA would classify it as a partial success. The SB-10 arrived on station on July 22nd and remained until August 6th, departing just as the recovery was finalized. Soviet naval intelligence reviewed the Glomar's activity logs and concluded the ship was conducting deep-sea mineral exploration consistent with publicly available records from the Hughes Corporation. The crew saw mining equipment, sample drills, and ore processing. They did not see the moon pool, the claw, or the submarine 30 feet below the waterline. The Glomar resumed its mining cover, then sailed to Hawaii, where the recovered materials were transferred to Navy intelligence under cover of darkness. The mission remained classified for 36 years. When the CIA finally declassified Project Azorian in 2010, it provided the first official confirmation of an operation that Soviet intelligence had reportedly uncovered as early as late 1974. The remains of 6 Soviet sailors were recovered from the forward section. The CIA, in accordance with naval tradition, arranged a burial at sea with military honors. The ceremony was filmed and later provided to the Soviet government as a gesture after the mission's declassification. Each sailor was wrapped in a Soviet naval flag and committed to the ocean from the Glomar's deck. A chaplain read prayers in Russian. The film remains one of the few public records of the mission's human cost. For the families of the K-129 crew who had believed their loved ones lost in an unexplained sinking, the burial footage provided closure decades later. The gesture did not erase the espionage, but it acknowledged the sailors as more than intelligence assets. They needed to know, could it have worked? The answer was complex. While Clementine's hydraulic pumps remained operational, the capture vehicle itself faced critical structural challenges. Historical accounts suggest the maraging steel fingers designed to grip the submarine proved too brittle under the immense load. The K-129's corroded hull certainly contributed to the failure, but the claw's fracture appears to have been the primary cause. The engineers documented numerous technical challenges at extreme depth, issues with visibility, the physical limitations of the grip mechanism, and the brutal realities of working in total darkness under crushing pressure. But here's what survived. Those findings became the blueprint. Modern deep submergence vehicles, commercial remotely operated vehicles, they all use pressure-compensated hydraulics now. Real-time force sensors, the technology that didn't exist in 1974. The Glomar Explorer proved covert recovery at extreme depth was possible, but only with adaptive control and instant feedback. They'd reached into the abyss and pulled up half a secret, and in doing so, they'd written the manual for every machine that would follow them down. The mission remains the deepest covert mechanical recovery in history. At 16,500 feet, Clementine operated at the edge of human engineering capability, in an environment where seawater pressure exceeds 7,000 psi, and visual feedback was severely limited by the technology of the era. No subsequent operation has attempted a recovery at this depth with comparable secrecy constraints. The Glomar Explorer itself was retired from covert service and later converted to a commercial deep-sea drilling vessel. Clementine was removed from the ship, with key components transferred to government archives and museums. The ship's moon pool, the largest ever built into a surface vessel, influenced the design of modern offshore drilling rigs and scientific research ships. The operational doctrine developed for Project Azorian, using commercial cover for intelligence missions, became a template for later CIA programs. According to technical accounts from the mission control room, pressure gauges read approximately 6,200 pounds per square inch when the claw closed around K-129. 8 days later, they showed 0 as the aft section fell back into the abyss. The mission recovered 1/3 of a submarine and 2 nuclear warheads. While some participants claimed code materials were found, official declassified histories state the codebooks were lost when the hull broke. The recovery also proved that blind mechanical recovery at crushing depth is possible, but only when the target is stronger than the ocean trying to reclaim it. The claw that couldn't hold on still accomplished the largest theft in naval history. The engineers who built Clementine knew the limits. Nielsen and his crew operated within them, made the decision to continue when the hull broke, and brought home enough to justify 4 years of secrecy, engineering, and risk. The remainder of the submarine section shattered into fragments across the ocean floor. After falling from the claw,